Hi class, this week's lecture is about grams to moles to molecule conversion. So if you're given a sample size and its weight, you should be able to calculate how many individual molecules or atoms are present in your sample, and vice versa. If you're given a number of molecules, you should be able to determine how much it would weigh. So in the laboratory, we actually don't count the individual particles or individual atoms, or if it's a compound, individual molecules. We look at them in a collective manner. So say, for instance, we have a sample of water like this much. All we do is just calculate the volume or look for the volume here from the markings. And from there, we can calculate the number of individual water molecules present in your sample. This actually contains billion and billions. So we just say water, but it actually contains billions and billions of water molecules. So we look at them in a collective group. Kind of like when you're baking. When you're baking big batches and you want to order eggs, for instance, you don't say buy me 60 eggs, right? You usually will request to buy 5 dozen eggs. And you know that a dozen, it's already a common knowledge that in a dozen, there's 12 individual eggs present. Similarly, in chemistry, we have our equivalent of a dozen. So we call this mole, okay? A group of individual particles is called a mole. A mole is abbreviated as MOL, and a mole contains this many individual particles. It's like a billion of a billion of a billion particles. So in your formula sheet, I actually chop this number down because contains a lot of numbers. We just drop the rest of the numbers here and then just got the 4 digits. Okay, so that's 6.022 times 10 to the power of 23. And it's right here on your formula sheet. Okay, so that's what that number means. It means that one collective group of sample or one mole of sample contains this many individual particles, 6.022 times 10 to the 23. Now, because this number is truncated, it's being rounded off, you must be very careful when you're using this number. You have to count the number of significant figures of a truncated number. So in this case, this number has 4 significant figures. Be very, very careful with that or using truncated numbers. In some textbook, this number is even rounded off further to 3 significant figures or even 1 significant figure. So you would see it rounded off as 6.02 times 10 to the power of 23, or in some textbook, it's just 6 times 10 to the 23. So be very careful when you're using numbers that are being rounded off, because when you're using that number in your calculations, you have to include or be very particular of its significant figures. Okay, we're going to have some examples to show you why you're going to have to be careful with that. Okay, so just to have a visual of what a mole of sample size looks like, I have here 8 different elements and what it looks like if you measure a mole of these samples. So a mole of zinc would look like this on a piece of filter paper, and this is a mole of carbon, pretty much your coal, a mole of magnesium shavings, a mole of copper wire, pretty much how many turns there are, a mole of sulfur, silicon, lead, and your tin. All of these samples contains same number of particles. It contains 6.022 times 10 to the 23 individual atoms. But if you look at the weight is different. Okay, the masses of these elements are different. And if you look and compare all of these 8 elements, your lead has the biggest weight. A mole of lead sample will contain 207 grams. It's kind of like measuring, the reason behind it is because of lead being the heaviest element or one of the heaviest element in the periodic table. If you measure 12 sumo wrestlers in a scale, it's going to be different. It's going to weigh more than if you weigh 12 marathon runners who are slim and skinny. Okay, so they may have the same quantity. They may contain 12, but then the weight, because it's a heavy sumo wrestler, is usually heavier in size or mass versus a slim runner is usually lighter in this case. So they will have different weights. So the heavier the atom, the more it will weigh. The heavier, it's going to reflect a heavier weight on the scale. So be very careful with that. Now let's try to do some calculations, shall we? Let's figure out how to convert or calculate the number of individual atoms present if you're given the quantity or your samples in moles. So let's start with the basic first, and then we'll move on to the chemistry aspect of it. So let's see. So say for instance you have 3.5 dozen eggs. You're asked to find how many individual eggs are present in 3.5 dozen eggs. To do that, we're going to use this as our conversion factor. We know that a dozen eggs has 12, so we're going to definitely use that in our dimensional analysis. How many eggs are there given 3.5 dozen eggs? Remember, you always need to find the given information and how to get to the unit. You're going to have to use a conversion factor. So here we know that there's 12 eggs in a dozen. I'm going to put 12 eggs up here, individual eggs, and 1 dozen down here. The reason why I put 1 dozen at the bottom or at the denominator is so that it will cancel off with the given information or the given unit. So the top and bottom must come from a given equation. Okay, so 3.5 times 12, that will give you a number. And the answer is 42 eggs. There are 42 eggs and 3.5 dozen. Now, look at this information. This information is an exact number. Okay, we know for a fact that a dozen contains 12, not 12.5, not 11.5, but exactly 12 individual pieces. So this number is an exact number. However, 3.5 is a given information and it's actually measured somewhere. So you have to count the number of significant figures. So this has 2 sig figs. So your final answer must have 2 sig figs as well. So that's 42 eggs. All right. So now let's do the chemistry aspect of it. How many individual atoms are present in let's say copper atoms are present in 4.50 moles of copper. So here we're given the group moles, 4.50 moles. You're asked to find the number of individual atoms present in that sample size. That should be atoms. All right, so how do we convert this? Given a collective group, mole, to its individual pieces, you're going to need the Avogadro's number. You're going to need this information right here as your conversion factor. Okay, so we know that a mole of any substance, in this case copper, contains 6.022 times 10 to the power of 23 copper atoms. Okay, again, the reason why I put 1 mole down here is so that it will cancel off with a given unit. So you multiply the number moles by 6.022, not divide it out. So I got 2.7099 times 10 to the power of 24 copper atoms. Now let's take a look at the numbers. So this number has 3 significant figures And this number is not an exact number, but rather a truncated or chopped off number. So this has 4 significant figures. So of the two, the one that has lesser number of sig figs is the given information. So we need to round it off to 3 sig figs. So 2.71 times 10 to the power of 24 copper atoms. Now, it's preferred that the number of signifigs for our final answer should be that of the given information. Or let me rephrase that. It's actually preferred that the limitations of when to round off your final answer must be dependent on the given or measured information there than the information that you can obtain from literature. Okay, so say for instance you have a measured value that is accurate to 3 sig figs. You don't want to use this data that is only up to 2 sig figs. So you don't want to use 6 times 10 to the power of 23. Why is that? Because now this is now the limitation, or now your final answer is now limited to this sig figs. If this information is given, you don't want to, you want as much as possible to be to have more sig figs on that information and instead of the given data. Okay, so try to avoid unnecessary means of giving you some smaller information or some inaccurate data, or obtaining an inaccurate data because of your literature. Okay, all right, so let's round it off to 3 sig figs, and that's going to be your answer. We can also do it the other way. If you're given the number of atoms, you're asked to find a collective group. How many moles of lead is present in, say, 4.853 times 10 to the power of 28 lead atoms? Okay, so you still use the same information. It's right here on the box to do that conversion. So this time, you're given number of individual atoms, and so the Avogadro's number, 6.22 times 10 to the 23 atoms, must be at the bottom in order to cancel with the information, and that the mole will be on the top. Okay, so the desired unit will be, which is moles, will be on the top. So in this case, you divide your information by 6.022 times 10 to the 23. So there you go. So you'll have 8.059 times 10 to the power of 4 moles of lead. So here's some exercises for you to do before we move on. Notice that this Avogadro's number is not only limited to the atoms. You can actually also describe it with any substances, may it be a compound. So if you're asked to find a mole of sodium chloride, it will actually contain 6.22 times 10 to the power of 23 sodium chloride molecules. So the only difference is that you're dealing with, if you're dealing with 2 or more atoms, or if you're dealing with a compound, you're dealing with 2 or more atoms, or we call that molecules, okay, or formula units for ionic compounds. So a mole of carbon dioxide will also contain 6.022 10 to the power of 23 CO2 molecules. Usually we call formula units for ionic compounds, compounds that contains a metal and a non-metal. Okay, so it's also not just limited to atoms or elements. It's not limited to the molecules or compound, but it's also going to be for anything, particles. Okay, so a mole of smog particles, that's smoke and fog combined, will contain this many individual smog particles. You can also refer them to ions. So a mole of sodium ion, that's a sodium element or sodium atom whose 1 electron is being removed. So will contain 6 billion of a billion sodium ions, okay, when we're dealing with electrolytes in our drink, for instance. Okay, so for this week, this is there's only two important things that you need to remember. And one of it is the mole to molecule or particle conversion. So a mole contains 6.022 times 10 to the power of 23. So who is responsible for choosing this really bizarre number? Why is a mole not a whole or fixed number like a dozen has 12 eggs? Why is it this number is such a weird or random number? The culprit or the reason, whoever the person behind this is actually Amadeo Avogadro. So he wrote a paper on this back in the day and then called the scientific community and he said, hey, scientific community, hey, fellow scientists, instead of counting individual particles, let's just call or collectively group them together and call it a mole. And a mole will contain 6.22 times 14076 times 10 to the 23 individual particles. And he didn't choose this randomly in order to spite the fellow scientists or make himself so controversial in that day. There's a reason or some scientific study behind this, and we're not going to get to that, but the main objective why the mole contains this rather bizarre number is because of this, or one of the advantages rather. The number 6.22, whatever that number is, times 10 to the power of 3, the reason behind that is so that that way he can quantify a mole or a group of individual atoms and measure its mass, and it's going to be easier to do and figure out its weight with respect to the weight of an individual atom. So let me rephrase that. By choosing one mole to have 6.22 times 10 to the 23, he can figure out the weight of a group of atoms. Okay, so one tiny carbon atom, for instance, will weigh 12 AMU, atomic mass unit. A group of carbon atoms or a mole of carbon atoms will numerically have the same number. It will also weigh 12, but rather it will have a different unit. It will weigh 12 grams. Think of it this way. Say a carbon atom is a piece of paper. When you put it on a scale or a big you can use the scale on your bathroom scale. If you put it on the piece of paper on your bathroom scale, it pretty much will, because it's so light, it doesn't reflect anything, right? It will say 0 right there. But if you have an actual scale that can measure a light material, it will reflect as 12 AMU. AMU is called atomic mass unit, and it will have this much equivalent weight of this in grams. Notice that this exponent is very small. That's because it's very, very light. Okay, now if you weigh a group of carbon atoms, in case a ream of paper, then it's going to start to reflect, and say it will reflect here now on your scale, and it will say grams, right? So now your scale can measure it, and it will measure as 12 grams, for instance. Now, so if you measure a little tiny carbon atom versus a group of carbon atoms or a mole of carbon atoms, it will have, numerically speaking, the same equivalent number, 12. But for a carbon atom, because it's so light, its unit is in atomic mass unit, which actually has an equivalent mass in weight in grams. And the weight of a mole, because it can now be registered, is going to be weighed as grams. Okay. So on the test, I might ask you to calculate the atomic mass of a particular element, and in this case carbon, then you would say 12 AMU. Where do I get that number? From your periodic table. So let's look at carbon real quick. Right here, notice that there's a number at the bottom of the element. That is the weight, or the average weight of a carbon atom. a single tiny atom will weigh 12.01 carbon. Now, it also is going to be the same number for if you're going to refer to a group of carbon atoms. So if you have a mole of carbon atoms, then it will also weigh 12.01, but in this time, the weight is going to be in grams because it's bigger. Okay, we call the weight of one atom the atomic mass. Makes sense. Mass of one atom. But we call the mass of a mole or a group of carbon atom molar mass, or abbreviated as MM or MW in some textbook. Okay, the mass of one mole. Okay, let's do some quick calculations real quick, okay, so that you can see the importance or the reason behind the novelty of this Avogadro's number. What is the weight in grams of carbon of one mole of carbon or a group of carbon? We know that a group of carbon or one mole of carbon contains the Avogadro's number, 6.022 times 10 to the 23 carbon atoms. We know the weight of a single carbon atom. One carbon atom weighs 12 AMU. Okay, and we know that an AMU, one atomic mass unit, is equivalent to this much in grams, 66053,904 times 10 to the power of 24 grams. So if we weigh that, we can calculate then the mass of one mole, and it will give you exactly 12.0 grams. Okay, so that's the reason behind it. So every time I'm going to ask you the mass of a group of atoms, you don't have to do this or perform this calculation. Simply look at the periodic table, look at the number below that element, and that will numerically have the same value as a group or an atom will have the same numeric value. The only difference is the units. One carbon atom will have 12 AMUs versus a group or 6 billion of a billion carbon atoms will weigh 12 grams. Okay, now in some textbook, you can see that the molar mass of carbon is written out not as 12 grams only, but it will have the unit 12.0 grams per mole. Okay, that makes sense. If you look at it, a mole, this is the weight, 12 grams is the weight of one mole of carbon. So if you're given a unit like this, gram per mole, don't be surprised. It just means that in a mole of carbon, there's actually 12 grams of carbon. It's basically just written out in one, instead of an equation, it's just written out in terms of a ratio, okay, grams per mole. So that is the molar mass. It will have the units grams per mole. Atomic mass will usually have the units AMU per atom. Now, when you have a substance that contains two or more individual atoms, you can also use moles when you're dealing with these groups of substances. So let's have some example below. So a mole of, when we're dealing with compounds, remember, if you recall, what is a compound? A compound contains two or more elements. Example is sodium chloride. Sodium chloride contains one sodium atom and one chlorine atom. When we're dealing with compounds, an individual compound is not called an atoms. That's atoms is for elements, right? So an element copper has, or one tiny element copper is basically called a copper atom, okay? But when we're talking about sodium chloride, an individual sodium chloride compound is called a molecule. Okay, a little sodium chloride molecule. Okay, so that's the smallest unit. So compound, one tiny compound is called molecule, whereas one tiny element is called an atom. Okay, so when we're dealing with compounds, a mole of compound will contain this much, or the Avogadro's number of molecules, individual molecules. So a single sodium chloride molecule will have a weight that is the sum of the weight of one sodium atom and one chlorine atom. So if you look at the periodic table, your sodium atom weighs roughly 23 AMU, and one chlorine atoms can weigh 35. So 35 plus 22.99, it will add up to 58. Okay, so the mass of one molecule is basically the mass of the individual atoms that is present in that molecule. For sodium chloride, it will contain one sodium and one chlorine. Now take a look at the units. The unit is still AMU because we're dealing with little tiny molecule of NaCl. In fact, we can't even see a molecule of NaCl. It's so small. This mass is called, the mass of a molecule is called molecular mass. It makes sense. The mass of one tiny molecule. Contrast that to the mass of an atom, okay? It's atomic mass, okay? But the unit is still AMU. So if you are asked to find the mass of one calcium nitrate molecule, then all you need to do is add all of the weight of all of the atoms present in calcium nitrate. So what is calcium nitrate? Calcium nitrate, calcium ion is Ca, nitrate ions is NO3 with an overall charge of -1. You're going to need two of these groups in order to neutralize one calcium ion. So the formula of calcium nitrate will be Ca, two of these groups, NO3, 2. Notice that I'm putting open and close parentheses because I'm dealing with two of these polyatomic ions. So the calcium nitrate actually contains, or one molecule of calcium nitrate contains one calcium atom. How many nitrogen atoms? 2 nitrogen atoms and 6. So you multiply that in. Then look at the periodic table. A single atom weighs 40.08 AMU. For nitrogen, that's 14.01. And for oxygen, that's 16. Get the sub-summary here and then add them all together. That will be the mass of your single calcium nitrate molecule. So I have here 164.09 AMU because we're dealing with tiny molecule. Now, if you're asked to find a mole of calcium nitrate molecule, then it will contain the same numerical value, 164.09, as the mass of the individual molecule, but this time around the units will be in grams. It's bigger. Okay, so going back for sodium chloride, the mass of one sodium chloride molecule is 58.4. That's the molecular mass, versus a group of sodium chloride, which contains this many individual molecules, will also have an equivalent number, 58.4, but the units will be in grams because that's the mass of one mole. So for this lecture, as I mentioned, there's only two things that you need to jot down on your notepad, and from there you'll be golden. The first one is to convert your moles to molecules, individual particles, using the Avogadro's number. Okay, so this is one of the important things. Sorry about that right there. And the second important one is to convert moles to its okay, that's actually that, moles to molecules. The second one information is actually the molar mass. Okay, and that can be done by looking at the periodic table. So two things is knowing how to convert a big group to its individual particles, or using the Avogadro's number, and the knowing how much that big group will weigh. Okay, so these are the two important factors that you will need to know. So we have what we call as a mole map to get you started. So once you have those two information, you actually won't need this mole map because it's going to be inherent for you, or inherent skill that you will learn time and time again. So to get you started, maybe just write this out on a piece of paper, and eventually you don't even need this map. Okay, so the mole map is to help you convert the weight to its equivalent number in your group, and from moles to calculate how many individual particles are present in that substance, and vice versa. If you want to convert moles to molecules, you need to multiply it out. But if you want to go the other way, you have to divide your information by the Avogadro's number. So you're going to need the Avogadro's number in order to do this. Okay. The next step is to convert moles to grams. So from grams to moles, I'm sorry, you look at the arrow. In order to convert grams into moles, you need to divide it by the molar mass of the substance, and molar mass of the substance can be found by looking at the periodic table. And if you want to do it the other way, from moles to grams, you're going to need to multiply it by the molar mass. Okay, say for example, I have 75 grams of silicon, and I'm going to be asked to find how many atoms are present in that sample. So I go to the lab, I measure 75 grams, and I can do that because I have a scale. But to figure out how many individual atoms are present in there, I'm going to have to do the calculation myself. I know by looking at the periodic table that silicon right here will have a weight of 28.09 grams. So that's that number right here. A mole will weigh 28.09 grams, not AMU, because we're dealing with group, okay, or something that is substantial. Grams, when you think of grams, you're thinking of a collective amount of your sample. So 28 down here, that way I can cancel it with the given information. Now that I have the information in moles, I'll convert that or figure out how many individual silicon atoms are present by using the Avogadro's number. So if you look at the mole map here, we go from grams to moles to molecules. So if we follow the arrow, we have to divide the grams at the bottom and then multiply it with the Avogadro's number in order to get this number right here. Okay, so it's a two-step process. In order to go from grams to molecules, this is the starting point, to this is the destination. It's a two-step process. You have to go through two arrows, okay? So you cannot just jump right ahead from grams to atoms by just one conversion factor. You have to go through two steps. You're going to need two information, the molar mass and the Avogadro's number. Let's try to do some example right here. So say for instance you measured in the lab 6 grams of sodium chloride. You're asked to find how many chloride ions are present in the sample. Remember, when we're having a compound, in actuality you actually don't have neutral atoms anymore. You have the ion versions of these elements. So sodium atom has already relinquished its electron and given it to chlorine. And chlorine atom is now gaining 1 electron, and so it now will have a charge of -1. So you have chloride ions present in there. So if you add the weight of sodium chloride, of sodium and chlorine, it will give you the weight of 58.44, numerically speaking. And if we're looking at collective group or a mole of sodium chloride, we're talking about the weight in grams and not in AMU. So remember your concept map here, guys. So we are given mass, grams. You're asked to convert it into individual particles. In this case, how many ions present? So let me just change that to particles. And in particular, we're dealing with how many ions are present. Okay, so to jump from here, you have to first convert it to moles. And from moles, you then can convert it to individual particles using the Avogadro's number. From grams to moles, you're going to need the information that will contain those two, and that will be your molar mass, grams per mole. Okay, let's try to do that. So you're going to need two information, okay? So this is one, the molar mass, and the second one is the Avogadro's number, which is 6.022 times 10 to the power of 23 particles. Okay, so let's start with the given information. 6 grams. You measure that in the lab, you have that on the scale, it's reflected on the scale, it's reflecting 6 grams. You know that a mole of sodium chloride sample will have a weight of 58.44. So on a scale, if it reflects 58.44, you know that you exactly have a mole of sample. But in case this is only a fraction, so you only have 6 out of 58. So you know that you only have a fraction of a mole. Okay, so how much of a fraction? Let's see, 6 divided by 58.44, you have 0.1 or a tenth of a mole in there. Okay, now you also know that a mole contains 1 sodium ion, I'm sorry, the Avogadro's number, 6.22 times 10 to the power of 23 individual sodium chloride atoms. Okay, now we'll do fine tune it. You're not asked to find the individual atom, but you're actually asked to find the specific number of chloride atoms. So just think of it as the sumo wrestler. So say for instance you have 2 moles of the sumo wrestler, right? I'm sorry, let's take it back. So we have that sumo wrestler analogy. We have 1 dozen sumo wrestler, and say you know its accumulative weight. Okay, in this case you are asked to find not just how many individual sumo wrestlers are in a dozen, but rather you're asked to find how many heads are in, how many sumo heads. Okay, a portion of that piece of body. Okay, so in this case you're not looking at sodium chloride molecule. I'm sorry, we should talk about molecule here because we're dealing with a compound. And then how many portion of that or a chloride ions is present in a molecule. Sorry, I'm just making it complicated to you guys, but let's see. 1 sodium chloride molecule contains 1 sodium ion and 1 chloride ion. Okay, so you're just looking at the fraction of it. So 1 sodium chloride molecule actually contains 1 chloride ion. Okay, so from here you'll able to cancel everything out, and what you're left is your individual ions. So we have, okay, so we have 6.2 times 10 to the power of 22 chloride ions. Notice that I rounded the number up to 2 sig figs based on the data here, or the one that has the least sig figs. This has 2 sig figs, this number has 4, that's 4, this number is exact. Okay, so that will give you 2 sig figs information. Let's find how many chloride ions are present in a 6-gram sample that's not from sodium chloride, but rather from something else. Let's take a look at something else here. Okay, so obviously you know what sodium chloride is, that's table salt. Okay, so if I measure 6 grams of table salt, um, that sample will actually contain 6.2 times 10 to the power of 22 chloride ions. Now let's take a look at other sources of chloride. So I have here another compound called calcium chloride. Okay, calcium chloride can be found mainly as a salt that you throw in on the roads to prevent ice. It's also very hygroscopic, meaning to say it really loves to absorb water, and so it can be sometimes be used as a desiccant. Okay, so when you see those little packets in your food, it contains calcium chloride, or sometimes silica gel. Okay, but calcium chloride is also one of the chemicals that can be used as a desiccant. This calcium chloride will have a molar mass of 110.98. So if you look at your periodic table, you will add one calcium and 2 chlorine atoms, and you will get 110.98. For a collective group of calcium chloride molecules, which contains the Avogadro's number, it will weigh same number, 110.98, but the units will be in grams. Let's figure out how many chloride ions is present in a 6-gram, same mass, 6 gram of calcium chloride. And let's try to compare that with the mass or with the number of chloride ion present in the 6-gram table salt, from the table salt. Okay, so 6-gram calcium chloride, we know that a mole of calcium chloride will weigh 110.98 grams. So a mole of calcium chloride has a weight of 110.98 grams. Okay. We also know that a mole of calcium chloride has how many individual molecules? It will have the Avogadro's number, 6.2223 calcium chloride molecules. Okay, now let's take a look at the individual molecule now. A tiny calcium chloride molecule, I'm sorry, has how many calcium ions and chloride ions? So let's revisit. Calcium chloride, calcium has a charge of 2 plus. Chloride ion is in group 7A, so it will have a charge of 1 minus. You're going to need 2 chloride ions to neutralize 1 calcium, and so the formula is 1 CaCl2, correct? So what does CaCl2 means? It means you have 1 calcium ion and 2 chloride ions present in that molecule. So in that molecule you'll have 2 chloride ions present. Okay, so that's 2. Okay, so if you do this calculation, you're going to multiply everything that's on the top and divide it with everything that's found in the bottom, and you're going to get a number. So I have 6.5 times 10 to the power of 22. If you look at these numbers, they actually are very much comparable. They are of the magnitude 22 and the values are around 6. Okay, so they almost have the same number of chloride ions present. And if you really just do this analysis without doing the calculation, you would think, if you look at the formula, calcium chloride has 2 chloride ions. It makes sense that it will have more chloride ion content than a compound that has only 1 chloride ion in that formula, right? So you are correct. If you think about it that way, you would expect that calcium chloride will have more chloride ions. But what you fail to forget is that the weight of calcium is actually heavier than a sodium atom. Sodium atom weighs around 23 grams, whereas a calcium atom weighs double that, around 40. So you also have to consider not only the number of atoms present in there or ions present in there, but also its weight when you're doing this calculation. But if you have a substance that has comparable weight, then of course, the more the number of chlorine atoms there in the formula, you would expect the higher the chloride ion content that formula would be. The reason why we're doing this calculation is there's one main importance, and that is, say for instance, chloride is very important piece of substance or species that you would need in order to perform other chemical reactions. And there's different sources of chloride in this world. Okay, so you have chloride from sodium chloride, the very easy source because you can easily get that from the kitchen, or chloride from calcium chloride, which is also an easy chemical that you can obtain. You can get any chloride from different compounds. Okay, and the most important thing is you want to calculate how much abundance of chloride ions are present in your sample. And not only that, is how easy is it to refine and process to extract these chloride ions from the compound itself. Sometimes it's not easy to remove this chloride ion from sodium ion, for instance, or chloride ions from calcium ion, for instance. Again, we're going to get to that later on. But for now, we just need to do some calculations. How can you calculate the specific content, okay, the most important ingredient from that compound? Can you compare it? Can you do this calculation, vice versa? Or let's do it the other way around. Say, for instance, you need a particular amount of chloride ions. I need to have 1 billion chloride ions in order to have this beautiful product and cure cancer, for instance. How much, or what is the weight of sodium chloride do I need in order to process or obtain this 100 ions or billion ions? So when we're dealing with a calculation like this, we're asked to find a particular atom in that molecule, or a particular portion in that sample. I'm going to show you the long method, and I'm going to show you a shortcut method to make your lives easier. Okay, so I'm going to do the long method first, and this is how your textbook will do it. And so that's easy for you. If you're going to go and read your textbook, it's very easy for you to analyze these things. And then I'm going to show you the shortcut method. Hopefully you can make sense of how easy it is with this shortcut method. So let's do the long method first. So this is pretty much the same as the last one, but in this case we're using barium chloride as our source of chlorine. And you're asked to find the individual chlorine atoms. Okay, so sometimes it's on the text you're asked to find chloride ion, or sometimes chloride atoms. That's fine. Okay, the only difference between the two is that chlorine atom is a neutral atom, whereas chlorine ion means that it has gained that electron. And remember, gaining an electron in terms of masses, the weight of a chlorine atom, which is a neutral atom, and the weight of the chloride ion, which is ionized, which gains 1 electron, is not really that different. Why? An electron weighs pretty much nothing. Okay, the reason why your atoms weighs a particular mass is because of the neutrons and the protons that is present inside the nucleus. So even if it has gained 20 electrons or removed 20 electrons, or how many electrons it has being transacted, the transaction during the chemical process, the weight stays to be the same because your electrons weighs pretty much nothing. Okay, you're asked to find how many chlorine atoms are present in this sample of substance, 6 grams barium chloride. Now look at your concept map, grams to moles to molecules or particles. I'll do molecule, instead of molecules, I'll change it to particles, because like I said, we could be dealing with a substance that is made up of element, or a substance that is made up of a compound. And so I'm just going to write it as particles. Okay, so you're going to need the molar mass to do that conversion, and from moles to particles you're going to need the Avogadro's number. So you're given this is your given information. you're asked to find the individual particles, and not only that, individual atom inside that molecule. Okay, so a few things, calculations to be done here. So let's do it one step at a time. We'll first convert our mass to its individual mole. Calculate to its moles by using the molar mass. The beauty is it's given right here. If it's not given, it's okay. All you need to do is go to the periodic table, add up the mass of barium and 2 chlorine atoms, and you're going to get 208.23. Chances are, if you're going to be given this type of calculation on the test, I will provide this information for you so that you don't have to look for it yourself. So the thing here is to break this information down. This means that 1 mole of your substance of barium chloride contains or has the mass or weight of 208.23 grams. Okay, that's what molar mass means. You need to know which one goes at the top and the bottom of your dimensional analysis. You know that the mass has to go down here because the given information is in grams. So you have to divide it by the molar mass. 1 mole goes on top. Remember, molar mass is always the mass of 1 mole. Okay, so you put 1 mole on top right here. Now that it is in moles, the next step is to convert or figure out how many molecules is present in that compound. Okay, barium chloride. A mole of barium chloride has how many molecules? The Avogadro's number, 6.22 times 10 to the 23 barium chloride molecules. Now, why did I put the Avogadro's number up here in the numerator? Because the given information prior to this is moles. That's why moles has to be down here. Okay, then you'll have this many molecules. 1 barium chloride molecules. Let's look at the component. It contains 1 barium atom or barium ion plus 2 chloride atom or 2 chloride ions. Okay, so then 1 barium chloride molecule. Which one are we more concerned of? We're concerned of the chlorine right here. So not the barium, but rather the chlorine component. So there's 2 chlorine atoms present in a molecule of barium chloride. So let's do that calculation. You're going to end up with a number. So we have here 2 sig figs, 5 sig figs, 4. Remember, this is the individual component. That's an exact number. So we'll have 2 sig figs right here as our final on our final answer. So it contains 3.5 times 10 to the power of 22 chlorine atoms in a 6 gram barium chloride sample. Now, what way can the number of chlorine atoms increase in a sample? It will increase if you have more of your sample. So instead of 6 grams, if you have 12 gram sample size, of course, the number of chlorine atoms there will also double up. It will double up if you have a different source of substance. If you have a different substance that will have more chlorine atoms and the weight is comparable, then the number of chlorine atoms will significantly spike up. It also will change if the weight of that other substance or other source of chlorine is going to be different than 208.23, and chances are that will also be different. Before we move on to that though, let's summarize what we're doing here. Okay, so remember the mole concept map or the mole map. So to go from grams to moles to particles, if you could do that for a compound, or if your substance is made of an element, you could also do that for your atoms, grams to moles to atoms. So let me just replace the particle to molecule for a compound, and for elements we're dealing with atoms. Okay, now when we're doing figuring out the specific component in your substance, in this case your chlorine ion or chlorine atom in your sodium chloride compound, you actually can put the tandem or the mole map in tandem. Okay, so you have this mole map for your compound, that's your sodium chloride, and this mole map for your element, and in this case, your chlorine. And if you're given the mole of your compound, you can actually go to and figure out the mole of the element through this way. Or if you're given the individual particles or molecules, you can calculate the individual atoms. So let me explain. So you have the mass of your chlorine. Let me change the color here real quick. You started with the mass of your sodium chloride. Okay. Okay, started with a mass of sodium chloride. You figure out how many moles are present in there. So you went to this pathway. And now that you know how many sodium chloride moles are present there, you figure out how many individual molecules are present. So you went further to this route right here. Now that you have the individual sodium chloride particles or sodium chloride molecules are present, you can then calculate the amount of sodium chloride ions present. So the route that you chose is from grams to moles to molecule, and from molecule to number of chlorine atoms or chlorine ions in this case. Okay, so that's the pathway. You can actually also go from this path, grams to moles and moles to moles of the element, and then that direction. So it's kind of like driving. You chose that as your map, okay? All right. Now, I'm going to bring this again and give you a different problem and then show you the shortcut. So we're now going to the shortcut method, okay? But copy this mole map for now. So this is like a pathway or a route. That way you don't get confused. Okay, so this problem right here is a little bit different from the first one. The first one, you're asked to find how many ions are present in a 6-gram sample. Here you're asked to find, sorry, same problem. Let me change it. Actually, it's different. Sorry, wrong slide. It's this one right here. So this is different because the first one you're asked to find how many ions, chloride ions are present. Here you're asked to find the weight of your chlorine atoms in a 6-gram sample. Okay, so the mole map has been complicated, starting with the compound, and then you have the individual component, in this case your chlorine. Okay, so we've shown that earlier. Okay, so you're asked from grams, so the pathway goes like this. And ignore the solution there already. You can already look at how the problem is being solved. But here you're given grams, and then you're asked to solve the number of grams of the individual component, in this case chlorine. So my pathway is to go from this route to moles of the barium chloride substance, and from there go down to go to the individual component, and from there calculate the individual grams. Okay, so that's the pathway. So from grams to moles, I'm going to need the molar mass of that compound. We know that the molar mass is 208.23. For those of you who don't know where that number came or how I came about that number, I basically look at the periodic table. So I know that the formula of barium chloride is BaCl2. It contains 1 barium and 2 chlorine atoms. So by just multiplying the chlorine by 2 and adding it with the barium atom and add that up, you get 208. Okay, so 208 grams goes down here, and 1 mole is going to go on the top. And the reason why I put the grams down here is because the information is in grams. If it was in moles, then that would be reversed. Okay, now I've calculated the amount in moles. The next step is figure out how many individual moles of chlorine is present in the compound. 1 mole of barium chloride will contain 1 mole of barium atom and 2 moles of chlorine, because we're looking at the collective group, okay? So that's 2 moles of chlorine. We know that a mole of chlorine will weigh how much? 35 grams. That's the molar mass of your chlorine. Molar mass of chlorine is 35.45 grams per mole. I got that from the periodic table. So 3 arrows to get to the mass of the individual component. That means there's 3-dimensional 3 conversion factors that are used in the dimensional analysis. So I got a number. So I got 2.0429, a really big number, grams chlorine. Now, if we look at the sig figs, we need to round this off to 2 sig figs. So it doesn't necessarily mean that it's the given information. Be very careful, like I said. You might use an information that is actually truncated. And so then your final answer will rely on that data. So here, 2 sig figs, 5. This is an exact number. This has 4. So your final answer should be rounded off to 2. So that gives you 2 grams chlorine. Let me just calculate it just to make sure that I got the number correct. Divided by 208.23. Okay? 2. Okay. Now, that is what is asked for. Okay? So if the question could be how many individual particles are present or chloride ions are present, just like in the previous problem, the pathway, remember your pathway could change. So in our earlier problem, say how many chlorine atoms are present. So you could go from this pathway and then down. Okay, that's 1. Or you could go this pathway and that. Okay, so it depends on which route you're going to take. Okay, just know that to go from grams to moles, you always need the molar mass. And in this case, for the compound, then moles to moles, and then moles to particles. Okay. In the previous problem, we went a different route. We went from grams to moles to particles and then to particles, or the individual atoms. All right. Now the shortcut method. When we're dealing with a compound and its components, if you take a spoonful of barium chloride, the mass ratio between barium and chlorine is always in the ratio of 1:2. Okay? For every 1 barium atom, there's always going to be 2 chlorine atoms. So even if I have a spoonful or a bag full or a house full of barium chloride sample, the ratio of barium to chlorine will never change. That's because that is the identity of your substance. So for every 1 barium atom, there's always going to be 2 chlorine atoms. The weight of 1 barium atom is always going to be 137 grams. And the weight of 2 chlorine atoms is always going to be 70 grams. So for every 137 grams of barium, there's always going to be 70.9 grams of chlorine attached. Or another way of thinking about it is for every 208 grams of sample, there's always going to be 137 grams of barium, or out of the 208, 137 grams of that is from the weight of your barium, and 70 grams of that is from the weight of your chlorine. So if I'm going to do the shortcut method, I have 6 grams of this sample, and I'm asked to find how many grams of chlorine or the individual component is present in that, then I'm just going to use that mass ratio. For every 208 grams of the sample, barium chloride, there's always going to be 70.9 grams of your barium. Chlorine. And if you do that, you're still going to end up with 2 grams of chlorine. Notice how this bottom one is just a shortcut of this longer method. 35.45 times 2 is your 70.9. And the 208 times 1 is that 208 down there. Okay, so I'm using this case for the component to be able to calculate the mass of the component from your sample. I'm using the mass ratio, not the mole ratio. In your textbook, they're always using mole ratios. Okay, the mole of your how many moles is present of the component is present in the substance, mole of substance. You don't have to go there. You can always use the mass ratio, because the analogy is the mass of your component is always going to be the same. The mass of 2 chlorine atoms is always going to be 70.9. You didn't change the mass. You didn't change the mole ratio. It's always 1:2. So that means the mass shouldn't change either. It's always going to be 137:70 grams. Okay, so let's do some exercises so that you can figure it out and basically master this. Okay.